Today's topic will be about applications and challenges of deep learning in medical image analysis. The title itself is very clear that our focus is on the medical images. So what is a medical image basically? And what purpose or for what basic needs we are going to use these medical images? For visualizing the medical images, we need to go for some set of analysis. And what are the various approaches we have for medical image analysis? The whole scenario is directly linked to deep learning technologies. So during this scenario, so what are the challenges you are going to encounter when we are practically implementing or when you are practically writing the papers? And what are the major applications of these medical image analysis? We'll try to cover in this lecture. I hope I'm audible and clear to all of you.
Yes, sir. You are audible, sir.
So moving further, first let's see about two types of systems. One is human system and the second one is let it be a deep learning system or AI system or computer vision system or whatever it is. Our objective is to identify a medical image. If a person or a layman or a human being is seeing an image, let it be a medical image. So we're able to see the particular image with the help of our eyes. When we are seeing with the help of eyes, definitely it will be processed with the help of our brain. The brain will come out with a decision which we'll be calling it as an intelligent decision. For example, I'm seeing a chest X-ray image. I'm able to see as a doctor or as a layman, I can able to see some set of fractures on the image. My decision will be there is a fracture in the chest part or rib part somewhere. This is how a human decision will be taking place. The same replica of the human decision system, we have something like deep learning system. Here in the place of eyes, the camera will be capturing the system. A satellite is a camera, a radar is a camera, anything, whatever your MRI scans, whatever it is, whatever your X-ray, everything will be a camera. In the case of a human decision system, your eye is a camera. Here the mechanized system is a camera. In the case of a human decision system, the processing unit will be your brain, whereas here you are using the image processing techniques. In this image processing techniques, you'll be seeing about various analysis techniques. Whereas in the case of a human decision system, the human itself is giving the decisions, which we'll be calling it as intelligent decisions. Here we'll be processing with the help of advanced deep learning algorithms or computer vision algorithms, whatnot. So for getting the effective intelligent decisions. So this is about the basic scenario or the basic introduction before taking place. So I'm saying about two technologies. In the case of image analysis, one is image processing and the second one is DL algorithms. Are both the same or different? In the case of a deep learning, input will be image, output will be interpretation, which is nothing but your result. You are going to analyze the things. The entire part medical image analysis will be happening in the deep learning stage. Here you are going to do image analysis or image interpretations. Interpretation is nothing but decisions or some set of rules, and you will be understanding the scenes or scenarios. Whereas coming to your image processing, the input is image and output is image. So why you are doing this image processing for medical image analysis is sometimes you need to recover some set of images. You need to reconstruct some images. There will be some set of noise. You need to remove. For that, you will be going for filtering. The sizes will be very high. You need to compress. You need to understand what class, what category, how much data we have, we need to go for some visualization. There are multiple things: image recovery, reconstruction, filtering, compression, visualization. For all these things, you'll be going for image processing. So once you have all these things, whether it may be image recovery or reconstruction or filtering or compression or visualization, then you need to go for analysis, which is the last step. For doing this analysis, we'll be using some set of deep learning techniques. Now coming to the core concept of medical imaging. So what is the need? Why you want to go for medical imaging? So medical itself says that there is something like diseases. When you have a disease, you need to go for some sort of treatments, some precautions, some monitorings are very much required. So this medical image analysis is very important and one of the necessity factor for diseases diagnosis, planning of the treatments, and monitoring of the diseases. As we have seen the previous slide, the analysis of the images, let it be medical or whatever it is, will be done by making use of deep learning. The reason why everyone in the today market are only approaching deep learning is because of its accuracy, which is one of the very important factor whenever you are developing a model or a method, the efficiency, the automation systems, and the error rate of the system, ROC curves of the system, how exactly you are segmenting the system, images, how exactly you are analyzing the images. So all these things, because of all these factors, deep learning has becoming a revolutionary factor, especially in the industry 6.0 era. Now we are in the industry 6.0 era. Now in the deep learning, so what we have to, what are the various approaches we have for medical image analysis? We have many techniques, which is commonly things which you all know about it. Convolutional neural networks, units, GANs. There are many advanced features in the deep learning techniques for medical image analysis. Prior to this deep learning approaches, there are many tools in the online which are available to you. You will upload some set of image, and if you ask for some set of segmentation, it will do it without using the deep learning techniques. Without an algorithm, without a proper pseudocode, without a proper architecture, how far we are going to depending on those unknown models? So that is where the deep learning came into the picture. Why deep learning for medical imaging? Look at the statistics. Now we are in 2024. In the case of a medical imaging, basically we'll be focusing on 5 different scenarios. One is ultrasound images, CT scans, MRI scans, X-rays, and other categories. How the data is growing year by year, you can see here. If you look at the medical field, it is not only about the images, you have categorical data sets, you have numerical data sets, there are other data sets also. But when it is coming to a research point of view, 99% of the researchers are only opting the image data because it is abundantly available. Day to day, the data of the images are increasing. Look at the graph. By 2032, how many billions it is able to cross, how much of data we are able to accumulate it. So you have so much of data for analyzing the things. When you have so much of data for analyzing the things, you can able to build a better classifier. When coming to the medical imaging data sets, when I'm speaking about a terminology called as medical images, brain diseases, eye diseases, head diseases, neck diseases, chest and abdomen diseases, pathology related, blood related, bone related, skin related, heart related. Basically, these are the major things which we are hearing in our day-to-day lives. Now let us see about the brain diseases. If I want to go for brain diseases classification, so what type of data sets I need to consider? Obviously, it is a medical image data sets. So what are the sources? What are the various data sets available? What are the various data set names available for us is available in this particular slide. So if anyone is doing research, if anyone is writing the papers, this slide will be the base slide, especially for your dataset descriptions. If I want to work on a brain diseases, the major datasets available are ADNI1, ADNI2, ADNI-Go, Oasis, Oasis 2, Oasis 3, Tadpole, and others followed by MTOP. Basically, in the case of a brain diseases, we'll be calling it as Parkinson's, which we are listening in your day-to-day lives. Alzheimer's. Have a look at Alzheimer's papers or Parkinson's papers or brain-related diseases papers. You can able to see the data sets of Oasis or ADNI. These data sets are publicly available. Whenever you want to do any sort of research, you can able to download the research. We can able to download the data sets and you can start experimenting on it. Like this for each and every disease. So I listed some of the data sets which are publicly available. Next, how the deep learning methods evolved from beginning till date, especially for the medical analysis. There is something called as reinforcement learning, which is started in 1989 basically. So one of the reinforcement learnings is nothing but your QNNs. So before that, we have a basics of deep learnings. The actual deep learning starts with Q learning concepts. Now we have seen so much of CNNs. So most of us are known about CNNs. We are very much familiar with AlexNets, DenseNets, ResNets, VGG 16, 19, 20, 21, Inception Nets, Capsule Nets. Now we are seeing generative neural networks. Now the latest versions in 2020s, we have seen something like mobile with architectures. Everything is already available. How you are going to analyze the image with these particular models is very important. How many layers you are going to use. So when you are changing any one layer, how the model, how the network is classifying is very important. Especially if you look from the 2015 or 2014, we have vision transformer techniques which are coming, which came into existence. The major objective of this vision transformers is lightweight data transformers. These are also called as lightweight data transformers. When your data is light, when your data is limited, we'll be going for this set of models. The basic fundamental problem with the medical image analysis is data sets. Though I have listed so many of data sets, the number of instances, the number of images in the data sets are less. It is practically not possible to tell a system is more accurate with 10,000 or 20,000 set of images. The model should be very much trained, which will be having more than 10 lakhs, 20 lakhs of set of images, which you are unable to get it from the websites. So for that, for improving the performance, though we have limited sets of data, we have something like vision transformers, which will be majorly applicable for lightweight data sets. This is about the evolution of the data learning methods, deep learning methods for various medical analysis. So what are the major applications we'll see? The previous figure, diseases detection by making use of the X-rays, CT scans, MRIs, PET scans. The major applications will be COVID-19 detection by making use of the CT scans, brain tumors classification, that is brain disorders, Alzheimer's, Parkinson's, or whatever it is, diabetic retinopathy detection. So it will take use of the retinal images of the eye. So based on that, it will analyze the images and it will classify the things. Under the diseases, I'm saying about the diabetic retinopathy, which is known to all. Now the major research area in the diabetic detection is diabetic food detection. So most of the researchers are moving towards the diabetic food detection techniques. If you look at the major data sets, most of the papers they're working on retinal images. So diabetic footopathy is the most research topic which we're seeing it now. So one is detection and classification. So one category is segmentation. So what is segmentation? I'll show with the practical screenshots in the later stages. If you look at a satellite, let us take a satellite. A satellite is a camera at the end of the day. If it is capturing an image from the sky, so it will take green parts, which is nothing but your trees. Ocean's blue part. It will capture mountains, it will capture vehicles, roads, whatnot, everything it will capture. Suppose my application is related to something like weather forecasting. So when the satellite is giving me some set of image, my objective is cloud, but not the other parts like buildings, all those things. But camera doesn't know, right? So it will capture an image will be having everything. Now I need to identify the object, which is one of the major objectives of this FTP. How you are going to identify the object in the image is very important. So for that particular analysis, my object is cloud. For this particular analysis, my object is my particular medical disease. So I want to extract that particular part. So we have seen something like basic machine learning models or data mining techniques like clustering techniques for segmenting. So how far they are reliable? Moving further in the radiology and histology, we have something like mammogram images, especially for the cancers, biopsy images, how it is going to assist in the heart diseases. We have something like ECG analysis, again, which is an image, MRI and CTC based heart diseases diagnosis. If you keep all this at one side, the second side is personalized medicine or personalized treatment is happening with the help of deep learning techniques, which is one of the major application of the deep learning in medical imaging techniques, which we'll be calling it as precision medicine also sometimes. What are the basic architectures of deep learning in medical imaging? What we have now? So we have seen already in the previous slide. One is CNNs, units. Now we have something like GANs, vision transformers. We have seen auto encoders. We have seen. As per my scenario, so most of the models are completely, the efficiency of the models are completely depending on how well you are going to train the system. If your system is not overfitting and underfitting, you'll be getting a better result. So to overcome that overfitting factor, which I'm saying, we need to go for thorough medical analysis, thorough medical imaging analysis. So this will be taking place in the future engineering phase, which we'll be seeing now. So before that, we'll see the challenges in the medical imaging. I told in the beginning itself, the basic challenge is availability of the data. We have data, but the system should be trained in a very effective way. So that much of training samples we don't have. We're not finding it. 10,000, 5,000 is not enough to train the system. So for that, as the data is limited, one approach is transfer learning approaches we have. So we have seen in the flyer what are the various transfer learning approaches also we have. The second challenge is, first one is the limited availability of data. Second one is the model interpretability and explainability. How far they are transparent is very important. Security related, ethically related, computational complexity related, and hardware requirements. These are all the challenges in the medical imaging analysis. If you look at the hardware requirements, so whatever we are doing in the basic labs to our students or whatever it is nothing. So to execute at least 1 lakh of images, we need a GPU for sure. If you are working on some 100 to 200 epochs, so epochs and all those things we'll see later. So they are the part of your CNN models. So basically in the papers or somewhere we have seen about 1 to 10 epochs or 1 to 20 epochs maximum. So that will not give an accurate result. If you look at the top journal papers or whatever it is, the testings will be done on GPUs by making use of at least 400 to 500 epochs. They will be taking the average values. It is increasing the computational complexity directly or indirectly. Most of us are not having this hardware requirements, which is one of the basic problem. And one of the fundamental problem is we have one model, one data set. This data set might not be performing well on this particular model, but the other data set when you are using it is outperforming. For this reason only the federated learning concepts came into the existence. How exactly the image analysis system is working? First step is your data collection. So data collection is nothing but your collection of data. From where you are going to collect the data. Let it be from online sites, which are different types of data set names I have shown in the previous slides. Or from the known doctors through hospitals, you are able to collect the data. It is always suggested to go for a benchmark data, so which is already available in the online. Or else if you are able to generate your own real-time data, you can do it. If you look at the brain disorders, Alzheimer's data, so it can be done with the brain images, plus you can able to generate your own numerical or categorical data by discussing. I'm just giving a case study as an example. You can create a Google sheet. You can create a survey form with that by using different categories of people, and you can able to fetch for at least 50,000 to 1 lakh of records. Then you can able to say it as a real-time data set. If not, go for the data sets which are available as a benchmark data sets already. The second important feature is future engineering. We'll be calling it as, or also we'll be calling it as pre-processing. So the data set, whatever you are having, you are feeling that it is not enough. You are going for pre-processing. Not enough meaning in the sense the size is not good, which is one factor. Or you're feeling there is some noise, there is some disturbance in the data, then you'll be going for this future engineering. Or you want to remove something, then you'll be going for this pre-processing. Or you want to enhance the qualities, or you have to maintain the dimensions. There are many alternatives. For all these things, we'll be going for this pre-processing. In the data collection, it is a raw data. After pre-processing, this is the data which we'll be using for analysis purpose. Before using the analysis purpose, we need to extract the exact portion that is required to us for analysis. That will be done by segmentation, which is one of the objective of this FDP, that is isolating the objects. The major technologies for isolating these objects is one of the fundamental techniques in deep learning is GANs. At the end, once the data is pre-processed, once the data is ready, the final objective is object recognition, which is nothing but your classification. Let us go with the case study, simple case study. This is what we experimented actually. And this is one of the work in SCA papers, actually one of the in IEEE Access journals. This is related to Alzheimer's disease, and we have taken VHS3 data set. And it is having only 3000 images. This is how the initial data set is. The first challenge what we are facing when we are collecting this raw data set in our experimentation is, as per our experience, they are not in the same size. Whenever you are doing a medical image analysis, the fundamental concept is each and every image should maintain a common size. Better to go for 256 or 250 or 512 by 512, whatever it is, better to go for 256 by 256. And always it is suggested to maintain a common size, which is a standard size. The basic motivation or reason behind this resizing is computational complexity. So once this is done, according to my data, it is only 3000 samples. I'm not feeling that. So my training will be effective and my testing will be effective. So I want to increase the data set. The original data set is natural data set. Now I want to increase the data set, which is nothing but my artificial data set. I am able to create it. If you are creating an artificial data set from the natural data set, we'll be calling it as augmentation. What is this augmentation and why you will do this augmentation? Augmentation is nothing but basically you are artificially expanding the size of the training data set. How you are going to expand this artificially in the sense you are creating modified versions of the existing data. How we are going to do these modifications? We'll do some set of transformations. So what are the various transformations we have? Brightness, horizontal vertical flips, zooms, rotatings, sharings, flippings, or any other complex techniques. You can use some set of synthetic data by making use of deep learning techniques here. And the primary importance or goal of this particular image augmentation techniques is to increase the diversity and variability of the training data. When you are doing an augmentation techniques, when you are going for an augmentation techniques, you can reduce the risk of overfitting the model, which is very important. Basically, the training set accuracy will be 100% sometimes, and testing set accuracy will be less than 50%, which is nothing but overfitting scenarios. So to reduce the risk of overfitting, always it is suggestible in the medical images to apply augmentation techniques. So one image you have, the same image you can able to generate some 20 to 50 different versions. Some 3000 images into 50 will become 1,50,000 nearly set of images. So to generate this set of images, we have various approaches. That is what we are seeing. Brightness alterations, flips, horizontals, vertical flips, zooms, rotations, sharings. So all these techniques, the major idea or the major focus is to reduce the overfitting. And this data augmentation can be applied on various types of data. It's not about only on images. It can be on text. It can be on audio. It can be on time series data also. Mostly, this augmentation technique in the computer vision or deep learning will be using on images. Why this data augmentation is important? Why you are doing in the sense? Limited data availability. That means that in the real world applications, obtaining large and high quality data sets can be challenging, time consuming, and expensive sometimes. The second important problem is overfitting, which you have seen. The third one is with less amount of data, the model's performance will be low. So to improve the model's performance, this data augmentation is very important. The particular tasks, what the augmentation will do is image recognitions, object detections, sometimes natural language processing also. It solves your class imbalance mitigation. If you look at some set of data, there might be some scenarios. Let us say for my particular study, Alzheimer's and non-Alzheimer's. Let us say I have 3000 sets of data. 2500 samples are Alzheimer's and 500 samples are non-Alzheimer's. Will it be correct data? There is a class imbalance problem here. So this data augmentation will help me to overcome this particular class imbalance problem. So how it is going to overcome? So you will be applying any of the data augmentation technique on the minority classes. My minority classes, according to my example, is 2500 is for Alzheimer's, 500 is for non-Alzheimer's. So my data augmentation focus will be on minority class, that is non-Alzheimer's class. I'll try to increase my number of samples here. And one of the major benefit will be transfer learning. And what are the basic limitations with these augmentation techniques? The biases will be increases basically. So when you are keeping on increasing the number of data sets, the quality is one of the very important factor. It's not about you are generating randomly by making use of data augmentation techniques. So quality checks are very important, which is one of the major drawback with this. It's not about whatever the methods you are having to use. Some research and specialized techniques are to be adopted in order to increase your data sets. Right augmentation approach is very important. Let us take an example. I have a 6. I have a number 6 as in an image. This 6, if I go for rotation, top bottom, if I go for rotation, sometimes I will get it as 9. 6 and 9 are not same. So here the augmentation technique is fails. So you need to choose the right augmentation approach for the given problem always. The basic techniques will be calling the geometric techniques. So whatever we have discussed, brightness alteration, flips, zooms, rotations, sharings, croppings, scalings. So all these comes under your basic geometric transformations. Sometimes you will be going for color transformations also. Your brightness is a color transformation technique. Contrast adjustments, grayscaling. This is one of the approach. You'll be applying some sort of filters. You'll be blurring the images. You'll be sharpening the images. You can use some set of GANs, generative adversarial neural networks. So this is about your complete image augmentation. So image augmentation is one of the fundamental things in your data pre-processing. Moving further, so we have seen various image augmentation techniques, right? This is one of our original technique. We are applying some set of flip operation. So flip operation can be done in two ways. One is horizontal flip and the second one is vertical flip. So this is about your flip operation. You can see here in the example. So this is my original image. So after performing, so using vertical image and using horizontal image, this is the output. In the case of an horizontally, basically this is a pixel, image is a pixel. The rows will be reversed in the case of a horizontal flip, and the columns will be reversed in the case of a vertical flip. So at the end of the day, this will be converted into a matrix format. So in the case of a horizontal flip, rows will be interchanged. That is, rows will be reversed. In the case of a vertical, columns will be reversed. That is the fundamental logic in flipping. Next, rotation. So this is my original image. The rotation is nothing but moving the angle or changing the angle. It can be a positive angle or it can be a negative angle. Basically, it is a two-dimensional diagram. A two-dimensional can be converted into a negative side or it can be a positive side. In both the ways, it is possible. So this particular example, this is one image for me. So I'm converting into minus 15 degrees. This is the second image. Plus 15 degrees. This is the third image. Like that, for a single image, I'm generating two more images. Like that, any angle you can able to convert. If I'm going for 100 different angles for the making use of this single image, I have my 100 different images. Like this, my 3000 into 100 will become 3 lakh set of images, which will be helpful for me in analysis. Next, sharing. Look at the original image. After sharing, these are the images. What exactly the sharing operation will do is, it changes the x-axis and y-axis. The reason is I am saying that it is a two-dimensional image at the end, which is having two axes. One is x and the second one is y. You are changing the x-axis and y-axis. That is what happening in the sharing operation. This sharing completely deals with changing the size of the original image. Basically, that is one of the changing the size and changing the shape of the object, 2D object, by making use of your x-axis and y-axis is the primary objective of your image sharing. Grayscale mode conversions. Next, hue setting of an image. Look at the example. Hue setting is nothing but you are just changing the visibility of the light. So dominant color within the images will be seeing. Those have to be adjusted. If not, the analysis will go wrong. This domination of the colors will be adjusted by making use of the hue value. The basic concept, the basic points about these hue images will be color manipulations basically. So let us say this is red. Assume that this is the red in color. By adjusting the hue value, we can this red can become pink, this red can become maroon or whatever it is based on the lighting factor. So this hue will be used when you want to go for a color correction in the images or artistic style transformations in the images, or you want to do some data augmentations. Next, you have something like image brightness. So this is one of your augmentation technique. Similarly, you have image contrast techniques. So after applying these many techniques, your original images will be converted and these images are ready for the analysis purpose. So these are the pre-processed images. Once you have the pre-processed images, you will develop any one architecture of the CNNs. For this case study, I'm saying it as a mobile. For this case study, I'm using a mobile with architecture, which is the latest version of the CNNs. So we have the data set here. We have done some future engineering. So from the future engineering, the original images, we have augmented, we have class imbalance problems, we have data limited problems. All those things we have done by making use of data augmentation, class imbalance things. Now we have the clear cut data, which is ready for the experimentation. Now we need to train the model. For the training purpose, we need to have one CNN architecture. So for that, we are using the mobile with architecture. I'm not going in depth of mobile with architecture. So I'm saying the overview of the model. This mobile with architecture, basically when you have limited sets of data, this will works and this will outperforms in terms of your performance measures, basically, which you have practically experimented it. As we said in the beginning slide, we have a capture image. If it is a human system, it is an eye. If it is a deep learning system, it is a camera. This is how you have a data. Next is there your brain is transforming the things, and here the image processing is transforming the things. Your brain is deciding the things there, and your model is deciding the things here. So here we are having some intelligent decision, and here you are having some artificial intelligent decision, that is Alzheimer's and non-Alzheimer's. As a human, with a human system, you are accurate that with your eyes, you are saying that it is a bus, it is 100% accurate. It is a car, 100% accurate. But as a mission, you need to have test with some set of performance measures. There are many set of performance measures which you can see. So the most commonly used performance measure which is known to everyone: accuracy, precision, recall, sensitivity, specificity, AUC curve and ROC curves. So for this experimentation, so this is the results what we got practically. Alzheimer's with 98.5% 57%. So the reason why I am projecting this particular case study is when I am saying that OASIS 3 data set with 3000 records. 3000 records is not sufficient for a good model for suggesting a good model. So we need to go for augmentation techniques, but we haven't done any augmentation techniques in our experimentation. So we have for lightweight data sets, one of the best methods in CNNs is Alzheimer's fit. So we tested the same with the other vision transformers like vision VGC16, VGC19, VGC21, DenseNet, AlexNet, RensNet, GoogleNet. Most of the techniques we have tested and experimented, but we have seen that this Alzheimer's weight is getting the better results, particularly when the data set is small. So how this mobile weight is, this is the internal logic of the mobile weight. So you will not find majority of the papers with mobile weight architectures because this is one of the latest technique. So you'll find many number of papers with VG16, 19, 21, AlexNet, DenseNet, but mobile weight will be getting very less papers. We have multiple blocks here. Totally in the case of a mobile net, we are going with 9 different blocks, which you can see here. Mobile bit blocks. 9 different mobile bit blocks are there for processing the image. And this is the error rate when compared with other models. And this is one of the performance measure for precision. And I had done some experimentation for recall. And this is a specificity factor. Kappa score. These are the various performance measures what have been tested. The final conclusion of this lecture is, for this medical image analysis, your fundamental thing is data sets first. So most of the available data sets are limited. When you have a limited, go for lightweight vision transformers models for analyzing the things. Or if you want to go for a good experimentation with the GPUs and servers which we have, you go with data augmentation, which has shown various data techniques. You can use Google Colab. You can get it the codes and everything is readily available. You can able to do it. So my suggestion is always go for good amounts of data whenever you are going for a medical image analysis. The basic reason is with the medical image analysis overfitting of the data. The entire medical image analysis revolves around overfitting. So to overcome this challenge, we need to go for data augmentation. So how to do that? We have some approaches which you have seen. This is about the lecture. You are open for any queries or any discussions if you have. Thank you.
Participants, any queries? Please post in the chat box. Sir, still 10 more minutes is there. Any discussion with your PhD work, sir? If it is
No
possible.
problem, sir. I can discuss it based on their queries. We can have a discussion. That is my point. Actually, it's a two-way communication. I'm expecting some queries from them for discussion.
Yes, sir. Exactly what you said is correct, but it online mode maybe. Okay, I will. Participants, I sincerely request any queries or is very valuable experience is there from research and all the things. Can you please?
So I suggest if any one of you are pursuing your PhDs or writing the papers for the top journals or something, the collaborations is very important. And make sure that what type of data you are using in the paper. So most of us here are, most of you people are known about all these things. These are the fundamental things or basic things, whatever I'm saying. Your data set description is very important. So I'm the reviewer for many of the SCI journals. I'm the editorial board of many SCI journals, which I have seen it. It's just a suggestion from my end. Your data set description and discussion is very important. For analyzing the things, the first important thing is data sets. So what is the source of the data set? How many samples you are collecting? Is these samples are enough to experiment without any overfittings? If not, what you have done? The solution is augmentation. If you have done augmentation, are you done correctly? We have seen some example of flip 6. If I flip 6, it will go 9. 6 and 9 are not same. Flip will not work for changing 6. So this is very important in data augmentation. So are you rescaling the images to a uniform size? These are all the fundamental image problems. This is one data set problem. The second problem with the data set problem for the image analysis is class imbalance problem, which we are forgetting. How you are going to improve this class imbalance problem again with the data augmentation? The third thing is we are directly experimenting with some set of training and some set of testing. So what about various epochs? At various levels, we need to check the data results. So most of us will go for 10 or 20 epochs. It is not sufficient for 10 or 20 epochs. So for the tabulated, we'll be seeing 1 to 20 or maximum 1 to 10, 1 to 20. But 200 to 400 epochs, people are doing it. It is taking some set of time to run the system. If you want to go with some, let us say some 20,000 of images for at least 100 epochs, it is taking 48 hours in a GPU, which I have seen practically. This is one of the fundamental problem in the medical image analysis, which is a time consuming process. If you have done the scaling properly, the time will be reduced, but not drastically. It is taking time. These are the things which you need to keep in mind whenever you are doing a medical image analysis. So we'll be saying it is a pre-processing basically. Technically, it is not a pre-processing, it is a future engineering phase. Pre-processing is one of the phase in the future engineering. It's not about only noise removal, pre-processing what we are seeing. It's about noise removal plus increasing the data sets, identifying the relevant objects, which is nothing but a segmentations. All these factors are coming into your future engineering concepts. Once you have the future engineering concepts, you have the ready-made, it is an open fact. Many models are available. So you can download it and you can get it done. But the thing is, whenever you are keeping the architectures in the paper or whatever it is, I suggest to completely redraw it or try to experiment with an addition of at least one layer to the code, so that the results will vary in a very large scale, whether it may go up or it may go low. So that will be your model. Nowadays, we have seen most of the retraction notices we are receiving just because we are copying the same architectures. It's not about copying. Try to do some changes in the architectures. So we have only one CNN in the beginning. Just there is a change in the layers. Let it be max cooling or padding or whatever it is. One layer they are changing. A new architecture is coming to the model in the market. So this is how the actual research is moving. So if you need any sort of collaborations, all those things for research purpose, you can always reach to me via email. I'll be happy to help you. Thank you. So